We're going to move on to section 4.4. This is on the fundamental theorem of calculus. So if you think about that, the fundamental theorem of calculus, this is supposed to be the greatest thing that we have in calculus. This is the foundation, the fundamental ideas of calculus. So the question that we're trying to answer that this will allow us to do is, what is the relationship between anti-differentiation and definite integration? We've seen repeated symbols. We've seen that integral symbol appear. But remember, anti-differentiation, that is this process of finding a function whose derivative was the one that was given to us. So basically, we're reversing the derivative process, saying what function has a derivative equal to this. But definite integration, on the other hand, that's looking at areas or net areas between curves and the x-axis. So how is there any relationship between areas of curves and the function whose derivative is this random thing? How is there any type of connection between these? And so that is what the fundamental theorem of calculus part 1, there's going to be 2 parts by the way, part 1 is going to state. So if f is a continuous function on this interval a to b, and f is an antiderivative of this. So remember, f is the function whose derivative is little f. Then this definite integral, this area, this net area from a to b of f of x, this can be found by this process. This is some notation that we're going to be using. But the important part is that this is going to be this big antiderivative evaluated at b minus a. So to evaluate this now, we don't have to draw pictures. We don't have to do limits. Obviously, I might ask you to use limits and Riemann sums, and then you're going to have to go through that process. But if I don't tell you that you have to use limits or Riemann sums, then you can just simply find the function whose derivative was this, plug in this top number, plug in the bottom number, and then subtract these. So the important way that I remember this, the acronym, is I think TGIF. So TGIF, I remember top goes in first. So this top number goes in first, and then the bottom number goes in second. So TGIF, top goes in first. So let's see some examples of this. So if we're using the fundamental theorem of calculus, I want to figure out what function has the derivative equal to x cubed. So if you think back to all of the techniques that we did, we would, if it's something like x to the power of n, we would add 1 to the power, then divide by that power. So we would add 1 to 3 to get 4, and I would divide this by 4. But this notation, what this is going to do is I'm going to have this vertical bar where I'm going to go from -1 to 2. So I take this notation here, and now I do top goes in first. So I plug in 2 in for x. So I have 2 to the 4th over 4, and then I subtract off what I get when I plug in -1. So I subtract off now a -1 to the 4th over 4. And so 2 to the 4th is going to be 16. Divide that by 4, you get 4. And this is a 1/4. Because -1 raised to the 4th is a positive 1. So this is going to be minus a 1/4. So this becomes 15/4. And if you wanted to, you could draw the curve of x cubed, find the net areas, and see that it's still going to be 15/4. So the fundamental theorem of calculus allows us to do integrals this way. Now, next one here, if I take this integral from -2 to -1 of u minus 1 over u squared, this one we should rewrite as u to the -2nd. So we'll do that first. So I'm going to do -2 to -1. I have u minus u to the -2nd du. Then remember, we do the same rules. I add 1 to the power, I divide by that. In this case, u just happens to be my variable, so I'm just doing the same thing. So I add 1 to this power of u, I divide by that power. Do the same thing over here. I add 1 to get -1, and I divide by -1. And I'm evaluating this from -2 to -1. Then I plug top number in first. Remember, this is the whole expression I'm plugging in -1 into. So everywhere there's a u, I put in a -1. So I have -1 squared divided by 2. And then I'm simply just going to get rid of this negative and this negative, and it'll just make it easier. So I have plus a -1 over -1. So u to the -1, this is the same thing as just 1 over u. Now I subtract off this whole expression. I have to subtract off this whole thing when I plug in -2. So I have -2 quantity squared divided by 2. And the same thing over here. I have a plus a 1 over -2. So then I just simplify this. So I have a 1/2. I have -1. This becomes a 4 over 2, which is obviously 2, minus a half. So I'm going to get 2 minus a half. That's going to be 3/2. So I have a minus 3/2. So then if I take a 1/2 minus 3/2, I get -1. So this whole thing becomes -2. And then now this one, we did not have a rule for absolute value of x. However, we can use some of our intuition about how could I deal with this. So I can still use the fundamental theorem of calculus. If we remember the absolute value of x, that depends on if x is going to be positive or it's going to be negative. So if you think back, absolute value of x, this is a piecewise function where we get the same thing back if x is greater than or equal to 0, but we're going to negate negative numbers. So it's this piecewise function. So we're going to use the properties of integrals that we had to break this up into two cases. One case will be when it's negative, and the other case will be when it's positive. So this becomes the integral from -2 to 0 of the absolute value of x dx, plus the integral from 0 to 3 of the absolute value of x dx. Now we know, because this is always negative, it looks like negative x, because I take a negative of a negative to get a positive. So I have the integral from -2 to 0 of negative x dx. And then this, because x is greater than or equal to 0 on this interval, I'm going to just plug in x. I guess integral from 0 to 3 of x dx. And so this, now again, we just use our same rules, add 1 to the power, divide by the power. So I have negative x squared over 2. This evaluates from -2 to 0. And then I add on this one, x squared over 2, and this goes from 0 to 3. So you can have multiple things. You just deal with each of them separately and then add the total together. So I have, the top goes in first, so I have 0 over 2, and then I do minus whatever I get when I plug in this -2. So I have a negative of -2 squared over 2. That's the first. And then over here I have plus 3 squared over 2 minus a 0 squared over 2. So this is 0. This -2 squared becomes 4. Negative that becomes -4. Divide that by 2, I get -2, but I have a negative of a negative, that becomes a positive 2. And then this one, I have 9 over 2 minus 0, so I have plus 9 over 2. And so this becomes 13 over 2. And again, if you weren't sure how to check your answer, you could, again, just draw the picture. Think about what the absolute value of x looks like, and you're looking at it from -2 to 3. You have these regions. You have two triangles. The area of this triangle is going to be 1/2 the base times height. So this has an area of 2. Area of this one, 1/2 the base times height. This has an area of 9/2. You add those together, you get 2 plus 9 halves, you get 13/2. So all of this is interconnected with the antiderivatives with our areas through this magical fundamental theorem of calculus.